Okay, but today we're going to discuss the final topic for the midterm, which is next Monday. So the last topic is integration by parts. And again, in a few minutes, I'll say a few more things about the exam. So here, like that's so weird how that looks like with the lights. I'll try to use some color. Like you cannot notice that. So here, the thing with the integration with parts is like so far, like the problems we have been doing like about the volume or the area or the length of the curve, kind of like what can be a bit harder about them is kind of like setting them up. But once you have like the integral that you have to do, the integral per se is not that bad because usually what it requires is some sort of like use up and most. Integration by parts is kind of like the opposite, where like the setup is not too hard because like it will be like the integral will be given to you, like the one that you want to compute. The thing is like it can become like a black hole of time because like it can get more like algebraically messy. So here like it's a problem where like the algebra is kind of like messier, whereas in the previous problems we were doing like the algebra is not that bad. It's just kind of like how do you set things up? How do you find the correct picture? So like the difficulty for this type of problems is somewhere else. Um, so what I told you like during the last few minutes of the last class is that the way you should think about integration by parts is that in some way it is like the reverse of like the product rule for derivatives. So again, like if you the usual convention in this case for integration by parts, well, let me just first write that it is kind of like the opposite or like the reverse of the product rule. Okay, so usually when you have like the product rule, you tend to call the functions f and g, I guess for like historical reasons. In this case, the functions are called u and v. So like I'll write the product rule in like the version that I'll use it. So you have two functions u and v that depend on x. And the idea of the product rule is that it is a derivative of the first function times the second function plus the the first function times the derivative of the second function. Okay, so that is what the product rule says. And kind of like the way to think about this is that, when you have like an equation, like there are certain operations you can do to an equation. Like you can multiply both sides of the equation by a number like 3 or 4, or like, you could subtract both sides of like the equation by like a number also. Or you could square both sides of the equation, or you could take square roots to both sides of like the equation, or you could take natural log of both sides of the equation. Like, there are many operations like you can do to an equation, like as long as you do the same operation to both of them. So kind of like what I'll kind of to find like the integration by parts formula, what I'll do instead is kind of like integrate both sides of like this equation with respect to x. So what I'll do is integrate. Now we integrate both sides of the equation with respect to x. And I literally just mean that, like, so I'll take like the integral of the left-hand side So like the integral of the left-hand side with respect to x should be the integral of the right-hand side with respect to x. That okay? Does that make sense? So far, so good. Again, think about it no different. Like, also when in Calc 1, you had like an equation, you would take the derivative both sides with respect to x when you were doing like implicit differentiation or whatever. So like kind of like integrals work the same way. Okay. The idea is that the left-hand side is kind of like easier to understand because what does the left-hand side mean in this case? It means what is like an antiderivative? It's like a function whose derivative is whatever is inside the integral, right? Like that's like an antiderivative. So we're trying to find, it's almost circular because what it's saying is like, find a function whose derivative is the derivative of u times t, right? So what is a function whose derivative is the derivative of u times v? It's u times v, right? It's kind of like almost by, like, it's almost like circular reasoning. Or another way to think about it is like, the way the derivative is supposed to work is kind of like as a cancellation operation, like to the integral. So like when you have like I'm sorry about that. When you have like a derivative and an integral, the way they're supposed to work is that they cancel one another. So that you like, this kind of like disappears, and that's how you like end up with the stuff on the inside, which if you kind of like work it out, like it does, that is how it's supposed to do. Because like what's the derivative of 3x? That's just 3. And what is the integral of 3? That's 3x. Oh, plus a constant of integration, which right now I'm ignoring, but all that I'm trying to say is that like, the way derivatives and derivatives work is that when they meet, they cancel, kind of like exponentials and logarithms, right? Like it's kind of like the same idea. So the left-hand side gives you, this just becomes, all of this becomes u of x times v of x. Again, I could put like a plus a constant of integration, but like implicitly that will be like in the other integrals. And then what is that integral of a sum? That's the sum of the integrals. So I'll write this like this. Okay, and then the last thing I'll do for now is that I'll kind of revert back to this prime notation for derivatives. Just to write this in a slightly different way. So this will be, what is the u dx? That's u prime of x. So you get u prime of x times v of x. And the other one would be, u of x times v prime of x. Okay. That is just what you get by reversing the product rule. Okay, this is, if you take the product rule and integrate both sides, that's what what you get like automatically. Now, the point of integration by parts, and I'll kind of like illustrate that with a few, like that's basically what we'll do just for today, like a bunch of examples, like implementing this formula. But the idea of like integration by parts is that Okay, maybe depending on what u and b ends up being, like maybe one of these two like integrals is actually easy to do. And so essentially it gives you like a way to find a harder integral in terms of like a product and an easier integral. So like the idea of like integration by parts, like let me kind of like the idea is that maybe uh let's say the first one because like that's a usual convention like um that's the usual convention. So you say that maybe this the first integral oops, is easy or easier, let's just say. Yeah. Maybe the then the second one. And so that like this equation would allow you to kind of like find the answer for the second one in terms of like the product and the first one. So so we would solve, so we would use this equation to find the harder one. So essentially the way the integration, like, and this is how like, now, right, like the formula in the way we will use it for today. Um, so all that I said up to this point, was kind of more like as a motivation. Uh, this is kind of like how in practice, we will use it. So, again, we'll think about it as being a formula for the second integral, which I'll call this one. So I'll put this one like as being hard, and this one is like the easy one. So what the integration by parts formula says is that the hard integral, like the difficult integral to find, would be u of x times v of x minus the easy integral. Okay. So in order to like in practice, and you'll see this in a moment, but in practice, the way to use this is that you will have like a function that you're trying to integrate, which you have to write as the product of two things. One will be u, and the other one will be the derivative of v. So in practice, what you will have, what you will have is a function you're trying to integrate. Uh, and you want to write it as a product of a function and a derivative. You want to rewrite it or to express it as the product. Okay, in fact, this is like such a like literally this is like the only rule I'll use today. So I'll write it on the board so that I can refer to it more easily, because otherwise I have to be going back and forth to. So that is what the integration by parts formula reads like. If you think about it, there's kind of like kind of clever way to think about it is that it is, which is why the prime notation is nice, because it's kind of like a formula for what if you wanted to move the prime to the other factor, right? So here right now, the prime, right, indicating the derivative is on the second factor. So like what he said is like, okay, if you wanted to place, the prime in the other factor, which is here, that's how the two of them are related. So it's kind of like a way to kind of like move where the derivative is, like the derivative moves from like the second position to the first position, basically. Um, which again can be advantageous because there are functions which are easier to integrate than to, or sorry, easier to differentiate than to integrate. So let me give you an example about how this works, because like really like the only way to kind of like absorb this part is just like by doing like a bunch of examples. This is like, I do think like a place where you have to see like a lot of variation to kind of like get comfortable. It's kind of like similar to when you're like learning the chain rule for the first time. You do have to see like a few examples to kind of like figure out what the pattern is supposed to be like. Okay, so are there any questions up to this point before we kind of move to the examples? So far, so good. Okay. So let me start with example one, which let's say if I wanted to find okay, so so what is going on with this integral? So if you stare at it for a second, like the idea is to convince yourself, okay, I actually don't know how to integrate this. So if it were only x, that would be easy. If it were only e to the x, that would also be easy. Even if there were like a square here, if there was like e to the export, that would be easy because then you can make a u sub u equals x squared, right? And the u would be 2x dx, so like that would allow you to do a u sub. But with the standard rules that we have, we don't really have like a way to integrate it until now, because that's where the like the integration by parts formula comes in. So it is kind of like a product, right? So like the product, like what we're trying to integrate is kind of like a product of two things. The idea is like to regard one of the factors as a function and the other factor as the derivative of a function, which is kind of like what you see here. Like the first factor is like the function which we're calling u, and the second factor would be the derivative of another function which we're calling v. So like of course, like like I could have like here I'm kind of like writing it in a way that like when you write a product, you can write it in any order, right? So it's not like, the point is like if I had written it like if I write it this way, you might say, oh, then this means that this has to be u and the other one has to be prime, right? But if I had written it this way, then you could have said, oh, this one has to be u and the other one has to be prime. So what I'm trying to say is that what gets called u and what gets called v prime is in terms of what makes your life easier, not in terms of which one appears first, because like you can rewrite a product in different orders, right? So like the choice has to be made like in terms of like simplifying your life, not making it harder. Okay, so I'll try both choices so that you see like that one does make your life easier and the other makes your life harder. Okay, but it's kind of like important to know that there are two options here, and it's not that it's alphabetical, right? Like from left to right, like whichever appears as the first factor, like is u, because like it can be rewritten. So I'll kind of like I'll actually write first like the one that works, but you'll see in a moment how it compares to the other one. So option one would, again, like if I had written it this way, I would have called this U and then this one V prime. Okay. And then let me actually use, I'll use the color. I'll try to fix two colors for today. So I'll use blue and I'll use blue for Q and V prime and red for V prime. Okay. So if you look at the formula, and there's like a way to memorize the formula, which I'll tell you in a moment, uh, with the trick. But if you look at this formula, right? Okay. So if you call this U and this one V prime, so U times V prime gives you X times e to the X, which is perfect. That's what we had here. So according to the integration by parts formula, what is the answer? Like you have to, like the first factor is U times V, okay? So U is X, but what is V? What we have here is V prime. But okay, for the exponential, that's not too bad because like the integral or the derivative of the exponential, it's like the exponential itself, right? Like that's fine. So in this case, like actually, like kind of like an accident, like a convenient accident. You know, if V prime is it's e to the x, V of x is also e to the x, right? And just to kind of like write the other one, if U of x is x, then U prime of x is 1, right? So in this case, you get U times V, U times V is U times e to the x, right? So like in this diagram, like you know, it's kind of like this diagonal product, if you like. Let me let's put this in brown. And then you subtract like the U prime, what is U prime, which is 1, and what is V of x, which is e to the x. So you're subtracting kind of like the the product of the quantities at the bottom, like the second row, if you want to think about it that way. Then just kind of like continue here. This is x e to the x. Is that making sense? So far, so good. Questions about that? Okay, and this doesn't look that bad because like it's kind of like useful to compare the first with the last terms. Like, you know, this was like a harder integral and we kind of like traded it off for something that's easier, right? Because this is just like integrating e to the x. Like the integral of e to the x is just to the e to the x. So that gives you x to e to the x minus e to the x. And here at this point, after you finish doing all the integrals, then you do put like the plus c for like the constant of integration. But it's until like the very end. Before then, like it doesn't make a lot of sense to put it. And that is actually the antiderivative for x times e to the x. It's times e to the x minus e to the x. Okay. But of course, who would memorize that? No one, like, you know, you have to use integration by parts to figure it out because it is like a very specific like type of integral, you know. So in fact, this proves like we just found Is that okay? Is that making sense? Okay, so these, like again, kind of like the game, when you're doing integration with parts, you're playing a game where you have to rewrite this as a product in a convenient way. So I took the first factor to be U and the second factor to be B prime. But again, the product can be written in a different way, right? So if you had written like the integral in this way, if you had like swapped the order, you could have said, oh, maybe this should have been U and this one should have been V prime. And what I want to show is that that actually makes your life harder, not easier. Okay, so like what I'm trying to say is like it is not arbitrary what gets called U and what gets called V. You really have to think that would that make this second integral better or not? So what if you had called like option two? What if you tried like U to the X, E to the X, and V prime of X, E to the X. No, sorry, V prime of X to be like X. Right, so I kind of like, I'm just thinking that I kind of like wrote the product in the opposite order. So again, like these two have to multiply to the function you started with, right? So they still multiply to e to the x times x, which is what's in here or in here. So that's good, but what happens now if you try to apply the integration by parts formula? Again, when you do the, like, let me copy paste it one more time here. So whenever you do like the integration by parts formula, you also need like the derivative of u, which is u prime. In this case, it's e to the x, and you need the antiderivative, or like you need the function v. So you need to integrate v prime, and so v is x squared over 2. So again, like kind of like the way this works is like in terms of like a diagram, you multiply this diagonal, and then you subtract like the products. You integrate the product of like the bottom row. So if you multiply the diagonal, you get e to the x times x squared over 2 minus like the integral. What is u prime? U prime is e to the x, and then v of x is x squared over 2. Is that making sense? That's worse, right? Because now you have to integrate this one, right? E to the x times x squared over 2. That is worse. In fact, that is way worse than integrating this one, So you didn't make, you actually traded off like the integral for something harder, It is like, in fact, if you wanted to integrate this, like you would actually kind of like do this backwards, and then you do first this one using the correct integration by parts, and then like it is like it can, like that's what I'm saying. Like you can get stuck easily because you do have to know which is like the U and which one is the V prime. So it's not like arbitrary, like you have to ask, if I swap it, do I make my life easier or harder? So like this is like harder. So like that means that was not the ideal choice for U and V prime. So not the ideal choice. Okay. Um, Okay, let me do another one and then I'll give you like a way to memorize the formula that's a little bit more easy. So this is actually one that I had mentioned last time, but it's a clever trick, so that's why it's worth like redoing it. Let's say I wanted to integrate natural log of x dx. Okay, and again, the idea, if you want to use integration by parts, is to write whatever you're integrating as a product, right? And so this looks like a bit of a scam because if you only have natural log of x, where is the product, right? Like where, like you just have natural log of x. That seems to be just like a single expression, right? Like where could you, you have to kind of like break down what you're integrating as a product of two things, right? So the solution is that secretly one is always there. You can always multiply anything by one. So like there is a product there. It's just like what you would call like a silly product, but not like, it's fine. Like, you can think of this as like this, you can think of like natural log of x times 1 dx. Okay. And now you do have a product. And like surprisingly, that does like fix it, like in the sense of like allowing you to apply the formula. Um, so essentially, this is like a one way you can think of like which one gets called U and which one gets called V. So what you can like what you have to think is like, okay, again, like you have to imagine like swapping like if you call one u, then you would need the derivative of u prime in the next step. And if you call the other one v prime, then you need like the integral of it. So of these two, right? Like, okay, for these two, it's easy to take that either the integral or the derivative. Not too bad, either one. But for this one, we don't know that the integral, right? That's essentially what we're trying to find. Like, so if you were to try to find like the integral, you would get stuck. The only thing you know to take from this one is the derivative. So this one forces it to be u because you can find the u prime for the next step. So this one like that makes this become u of x. Okay, so for this particular problem, u of x is going to be natural log of x, and v prime is going to be 1. Okay, and again, like the kind of like the idea is to check that the first row multiplies back to the function, like the integral you started with, and then you take the derivative. What the derivative of natural log is 1 over x. Then you take the integral of the other one. By integral, I just mean like an antiderivative. We don't keep the plus c here, like it's just one that works. So what is a function whose derivative is 1? That's just x. So take x here. And again, the way like what the integration by parts formula says, yes, I think I can copy it again. What the integration by parts formula says is that at least if you kind of like arrange it this way, you multiply u with v, which corresponds to that diagonal. So you get, well, let me put it like this, natural log of x times x. And then you subtract the bottom, like the products of like the things at the bottom. So you subtract this one. So what is u prime? U prime is 1 over x. And what is v of x? That's x. So and again, that's supposed to be natural log of x times the 1 dx. That okay? And that made like our lives easier because like again, like this was just like integrating natural log, which we don't know how to do. And these it like after you simplify, it's just like integrating one. Like we do know how to integrate one. So um if you kind of like so like what if you kind of work well, it's kind of like weird to have like the x after natural log, so I'll just write it as x natural log of x minus the integral of one. So that gives you this very convenient formula for the integral of natural log, which is x natural log of x, plus the integral of one x plus a constant. Is that okay? Okay, now I'll give you another a way to memorize a formula, and then I'll do an example that is actually two examples which are like on the harder spectrum of like of these things. Because like they are like a bit more subtle. So like here's like a way to memorize the integration by parts formula. Ah, which it I mean I'm sure there are other like ways to read this, but it's like kind of like the ultraviolet voodoo trick. So what does that mean? If you kind of like go back just to go back to one of like the steps, when we were playing with this formula for integration by parts, uh it's kind of like a trick that you use. So if you go back to back some steps to this formula, and if you kind of pretend that for the moment that like the derivatives are some sort of like ratios, then you have like dx with dx here, which would cancel, and then you have a dx with dx here, which would cancel. So it's kind of like just like a way to memorize the formula. So if you cancel like cancel dx, you get u of x times v of x equals, so if you cancel the dx's, you get du times v. And then if you cancel the x's here, you get u dv. Okay. And this is kind of like u times v prime. I mean, dv is like v prime dx, in fact. So, and so if you kind of like rewrite it this way, you can say like, we like before we were solving for this quantity. So like the other way to write like the integration by parts formula is to say that u dv is uv minus, and like it kind of looks weird to have this way, like you put like the v first, so minus v du. So like I guess this is supposed to, like so it's like u dv is uv minus v du, or if you want like the ultraviolet is here and the voodoo is here. So like that's kind of like where the mnemonic comes from. So this one is like the ultraviolet, like the ultraviolet, and this is the voodoo part. Okay, that makes sense. So like, that is one way to kind of like think about the rule in practice. But it is the same idea. You want to break the product into something that is kind of like the function and the other one, which is like the derivative or like the dv. Um, so it doesn't matter like how you write it. Now, let me do two more, which are more complicated. So let's start with the first one. And this is kind of back to my point of what I was saying before, where with this is kind of like a topic where like there's so many potential variations where like I'm trying to kind of like show you an example of like each variation, but you do have to kind of like just go through like some of them to kind of get used to the different tricks. So I'm kind of like trying to show you like all the different tricks that typically show up when you're learning integration by parts for the first time, you know. But it can be like yes.
So this is not like a valid thing, right? Like we can't actually cancel with this. It's like this formula is not a valid formula.
I mean, it can be made valid if you talk about something that is called differentials, uh, which is something that has been dropped from like calculus classes, but it's still something that you can kind of like still like make sense of. So it can be made to work kind of like not just like as a, oh, here's like a trick that kind of like it's nice. It can actually be made to work so that it's kind of like more literal. But yeah, for now it's kind of like a linguistic thing, like, oh, we're just playing with the, how we're writing things. Because like if you write the derivative as a fraction, then like it does allow you to kind of like do those tricks. But no, they can be kind of like made more sense of. But you need something called like differentials for that, if that makes sense. Um, Also, before I continue, because I have been checking the weather app, depending on which one I check, there might be snow on Wednesday or not. I'm not sure. So like, I don't know if they will ask, like, if there's like an announcement or sorts, like asking the class to be moved online, that, it is what it is. But then I'll send you like an announcement like, and the Zoom link. But depending where I look for the weather, like either there's no storm or there's a snow or there's like a snowstorm. So like, we'll see. Like still have like 72 hours, 48 hours, I guess. But just keep an eye on it. Like I may send you like an email by the end of Tuesday, if, like send like an announcement about that. And also in terms of the exam, now I think now by now everyone should be here. But so I posted, like, can I show this? Oh yeah, you can see, is this class? No, this is not this class. So if you go to like, if you go, there's like a Canvas site for like all the Calc 2 sections where this is where like I got this, I posted this review sheet from. Now this review sheet, like, I mean, you should check it out, but like do kind of like go through like the one that I also created, because for example, I'm only going to ask things that I cover in class. So like I didn't really go into the average value of a function because I kind of consider that more like a Calc 1 topic. So I won't ask like a question about like average value. I think there's some of those here, or like kind of like area between curves. I didn't really go through area between curves because like again, it's kind of like something that I'm assuming you kind of like went over already. So essentially, if you kind of look at this review sheet, like you can start like with the problems that say section 6.1 forward. Like this one's from chapter 5. Like it was more like a review, but it's not going something that I will ask like directly, you know what I mean? And then but yeah, I'll kind of like write the exam so that it's very close to like the problems you have been seeing like in the workshop on like on the examples we have been doing. So I'll kind of like stick very close to that. I may probably just put one of those like literally copy pasted. So like now you have an incentive to go through all of them, because like I'll just grab like one from either like a workshop or like an example from class, and you'll find it there on the exam. But yeah, like I did kind of like make like a separate like like review, just kind of reminding you of like these identities are kind of like important. I mean, we don't really need like that, like from trick stuff. Like I guess like some of this will be not that, right now it's not super important, but you know, like there's some derivative rules in case, like, you know, you forgot about them. But you know, like, I'm just saying, like, in terms of topics, like what we have done is like, how do you find the volume if you take the cross section? How do you find the volume if you do like the rotation thing? How do you find the length of the curve? How do you find the area? And how do you do the integration by parts, which is what we're talking about right now. So that's kind of like the five main things that we have been working on, and that's what like the exam will be focused on. Yeah. I think I mean, actually, I can tell you that on Wednesday after finish writing it. Like, but I would go for 5 or 6, depending. Like, I'll have some repetition from integration by parts because that's kind of like important, and there's more ways to ask that. But yeah, like at least definitely one from each of the like, you know, one from cross section, one from revolution, one like length, one surface area, then that's 4, and then probably 2 from integration by parts. What I'm trying to kind of like think about is like, you know, there might be a problem where, like, for example, I ask you, oh, give the volume in 2 different ways, like, you know, set it up as an integral if you were doing the cross section method versus set it up as an integral if you were doing the solid revolution thing. So I may kind of like integrate some of those, but yeah, I wouldn't do more than 6 questions. But probably like, yeah, I think I'm going for something like that. 4 plus 2 from integration by parts. So, yeah, that's more or less my plan, but I can kind of like tell you that once I have written it. Yeah. Well, for like the volume ones, I'll kind of like be more like, oh yeah, show that say for something silly, like show that the volume of a sphere is 4/3 pi r cubed, you know, where it kind of like is left in terms of r. For the integration by parts, they would definitely always be numbers. And but yeah, for some of those, like there might be like, or like a cone where there's like the height h and the radius r, then I'd probably be more inclined to do something like along those lines where like it kind of is left in terms of those things. So like that's why I was saying like pay kind of closer attention to the workshop problems, because most of those were kind of like phrased in that same way. So but yeah, I mean, but there most likely would be one that's kind of more like just like but yeah, definitely for this integration by part formulas, like I would just put like, you know, like few numbers because otherwise it's a bit too messy. But yeah, but it won't be any, like if you have gone through all the workshop problems and the examples in class, the exam will be 100% predictable from it, basically, you know, like there wouldn't be like anything that should come across as like too surprising, you know what I mean? Okay, so yeah, like I want to do 2 more examples, but this one is kind of very interesting because again, like it can be subtle how you do the breaking. Okay, this one is interesting. I'll give you a second to think about it. Okay, so again, you have like, definitely, if you just look at this thing, there's no way to integrate that directly, like before integration by parts. That's for sure. So again, like the philosophy of integration by parts is like, let's break the function, like what you're integrating into 2 pieces, right? One, which is like the u, and the other one, which is v prime or dv, depending on how you want to call it. Now, for example, the way this is written, it would say, well, that means that either this one should be u or this one should be u, right? That's what you might think at first glance. Okay, so if you think like, for example, in those terms, you know, take something like x to the 7. Like x to the 7 is easy to differentiate, and it's also easy to integrate, right? So this one doesn't make too much difference whether you wanted to take it the derivative of integral. Now, if you take this one, right? This one is not easy to integrate. That you don't know how to integrate. And to take the derivative, you can take the derivative, but it kind of won't, I mean, it will be not that much better, if you know what I mean, because when you do the derivative rule, right, like this exponent gets dropped by 1, so this would become -1/3. And then you have to do the chain rule, and then you get like a 4x cubed from the chain rule. So like either like for the second factor, the derivative and the integral, they don't like the integral definitely we don't know how to do. And the derivative doesn't seem that would be that much better, right? So this one is kind of like not like a bit confusing because like the breaking, like like the natural breakup that you would try is not the ideal. So in this case, the trick is to say, oh, actually, this factor again, it's always easy to integrate or differentiate. What we want to do is kind of like somehow make this factor easier to integrate because the derivative is a mess because of like the chain rule and all that stuff. And so what would this make it easier to integrate if you had something that would allow you to do like a U sub, right? Like to integrate these things. So what would this like, if you thought about this like as a problem with U sub, you would say, oh, I would like to call U x to the 4 plus 1, right? But that because of the U sub method, like it would require like an x cubed, right? Like because of the du, it would spit out like 4x cubed dx. So what I would kind of like do is break this into x to the 4 times x to the 3. And that's kind of like the trick, which is kind of very clever. So I'll kind of think about it in this way. Like I'll write this as x to the 4 times x to the 3, x to the 4 plus 1 times 2/3 dx. So it's still like it is still the same thing. It's now by arranging it this way, this is easier to integrate on its own. And this is still kind of like easy to either integrate or differentiate. Okay. Okay. So what I'll do now is called u x to the 4. And I'll call dv or v prime, like I'll just call it dv for now. I'll call the rest dv. So if you want, it will be x cubed x to the 4 plus 1 to the 2/3 times dx. Oops, sorry about that. Okay. Okay, so this is the product gives you UDV gives you this quantity, so that's good. Okay, now what we needed is the derivative of u. The derivative of u, or now which we're calling du would be 4x cubed dx, right? And if this is dv, right? What is v? V, like again, like to find the antiderivative of this, you do have to make a u sub for this. It's kind of like a problem within a problem because this one would require like a u sub, which is a different u from this. Like there's no relation whatsoever in that case. But if you make a u sub, you can find that this is 3 divided by 20. X to the 4 plus 1 to the 5 halves. So like to find this, like you make a substitution. Make a substitution to integrate a u sub. Again, which has nothing to do with what we're calling u in this other problem. But again, at least you can double check that this like works because if you take the derivative of this, the 5/3 comes down, the 3's cancel, the 5 cancels like a 5 from the 20, so that gives you 1/4. The exponent drops to 2/3, and then by the chain rule, you get 4x cubed, so that cancels the 4 that you had left, and then you just get x cubed. So I mean, you can double check that this like does work, but if you wanted to find it like firsthand, like you would need to integrate that independently. Okay. Like actually, I can like write what the use of would be. And that's where that comes from. But like again, what like the thing is that once you have identified the U and the D prime or U and DV, then the rest of the problem should be more or less doable. Kind of like what requires some practice is like how do you do the identification? Because for example, this one did require this breakup trick, which is not super obvious at first. You kind of have to see it before like knowing that you have to be on the lookout for those things when you want to use them. So, but if you do this, like what is U and V? So UV would become x to the 4 times 3/20, x to the 4 plus 1 times raised to the 5/3 minus V du. Okay, so what is V? V is that thing. So and what is the U? The U is 4x cubed dx. Okay, so just to kind of like rewrite this a little bit better, so this becomes 3/20 x to the 4 x to the 4 plus 1 to the 5/3 minus, okay, 3/5, right? If you do the products of like x cubed, x to the 4 plus 1 to the 5/3 dx. Five divided by 3. Is that okay? Questions about this? And this is actually better because this can, I mean, this more or less can be found in the same way as this one before. Like, it is actually the same. I mean, the only difference is like, that this was 2/3, now it's 5/3, but the same U sub actually would work. So here you can do like a U sub x to the 4 plus 1 to integrate this piece. Like, the thing was kind of to realize that we needed a factor of x cubed to make the integration possible. So you kind of like grab it by force from like x to the 7 to kind of like make everything like everything work out. So here you would do like another U sub, like it's kind of like the same U sub UE, which is kind of like again like I'm not a big fan of the fact that these things are called U and V, but it's too like standard to it can be confusing because like the other thing is called U sub. So but the U's kind of have different purposes. And so if you kind of like do all of this integration, you end up with 3 divided by 20. Like I'll just write the final answer so that I can move to the last example I wanted to do for today. And so, but yeah, if you integrate all of this, you'll get like something like this. So this will become 8/3 because you have to increase the exponent by 1. And that is what you end up finding. So all of this equals the antiderivative of x to the 7 times what, like x plus x to the 4 plus 1 to the 2/3. Like, it is, again, like if we're not for integration by parts, it would not be like very plausible to find this like in terms of like a closed formula. So it is really like magical, like, like the integration by parts. Okay. Okay, last but not least, this one also requires a cute trick. So another one. And with these that I have done, all the others like fit into one of these cases, basically. So it's just like identify, like, getting used to how do I identify them. But let's say that I want to find e to the x sine of x dx. Okay, so this one is nice. It is a product in a clear way, and both factors are easy to take derivatives or to integrate, right? Like e to the x, you know how to differentiate, integrate. Sine of x, you know how to differentiate, integrate. So this one is actually more like a toss-up, like which one you want to call u and which one you want to call dv. Like they both more or less would work. I would just kind of like go with how I wrote it here. So I'll call u e to the x, and I'll call dv, I'll call dv sine of x dx. Okay, and then this is u. So again, one gets differentiated, which in this case would be du. So du is e to the x dx. And the other one gets integrated, right? So what is the integral of sine of x? That's negative cosine, right? So again, like UDV, what integration by parts says is like ultraviolet voodoo. So ultraviolet is like UV, and the voodoo is VDU. Okay. So this is telling you that e to the x sine of x, right? So is UV, so again, it's kind of like the diagonal. UV is e to the x times negative cosine of x minus v du. V is negative cosine of x, right? And du is e to the x dx. That okay? Is that making sense? Okay, so before continuing, I'll just kind of like, there's too many minus signs, like, which are kind of annoying. So what we found so far is that this is negative e to the x cosine of x, and then minus minus becomes a plus, so plus cosine of x e to the x dx. Okay, so far so good. Okay, so this is interesting because, like, we replace this integral by this integral, which is kind of like in terms of difficulty, kind of like looks more or less the same because, like, it has both have like an e to the x, and okay, you're replacing a sine with a cosine, but sines and cosines are not that different from one another. So at this point, it's not clear whether there's like an improvement or not, but now like in this case, like you just have to keep going. So I'll just try to do integration by parts to this one again. And that's where like the fun thing happens. So just for consistency, it seems like I was calling u the exponential, I'll just keep calling u the exponential and dv like the trig stuff. So, okay. So I'll put this like on hold because I'll have to return to this one. So let's on hold, and then I'll try to find now kind of like, as again, like a problem within a problem. So I'll try to find cosine of x e to the x dx. So you get here what? So like again, if I make u of x e to the x just because that's how I did it last time, du would be e to the x dx. And then I'll call dv the remaining stuff. So dv would be cosine of x dx. And so v would be sine of x dx because like sine of x because like the integral of cosine is sine. Okay. So again, like what integration by parts says is that this integral should be ultraviolet voodoo, so it should be uv minus v du. So what this is saying is that cosine of x, okay, I'm almost done. Cosine of x e to the x dx is what is uv is e to the x sine of x minus the integral of v du. What is v sine of x? And the u is e to the x dx. Is that okay? Is that making sense? So far, so good. And now here's like the fun part because it looks okay. Like it feels like are we going in circles? Because now this one has to be computed in terms of this one, and you're like, okay, this is like again, like this is not going to work. But you don't have to like become desperate. Like the idea is like again, this we were trying to find this, and so you kind of like put it back into the box, like that formula. So kind of like insert this formula. It looks like circuit, like it looks like you're going like back to where you started, but actually you're not. So substitute this into, let's call that asterisk. So if you could call this asterisk, this is saying that e to the x sine of x dx would be minus e to the x cosine of x plus like this integral, which we just found. Oops, sorry about that. And then this is the cool thing that, yeah, like this same integral appears on both sides of the equation, but because this one appears with a minus, I can move it to the other side as a 2 times that integral. So that means that 2 times the integral of e to the x sine of x dx, is minus e to the x cosine of x plus e to the x sine of x. And then to solve, you like divide by 2. So e to the x sine of x dx is 1/2. Well, you can also factor a cos at e to the x if you like. So, and don't forget to put like constant of integration somewhere towards the end. Like, like you don't have to carry it until like the very last step. Like who cares about that? Like, but this is like also like what makes this one also interesting is that it is one where like, it feels like you're going like returning to where you started, but because like the integral reappears with the opposite sign, you can kind of like combine it with what you had like originally, and that makes it work. Okay. And for any of these, like again, like it's always fun to double check that if you were to take the derivative of this function, you would find e to the x sine of x. Okay.
So you said that like for every example, you're kind of trying to go through the different scenarios.
Right. Look, so the 4 scenarios are, what are the 4 scenarios? Let's see. Okay. Scenario one is like where like literally it is just like the integration by parts formula without,
And
right, like without any tricks, right? Like it's like the no tricks form integration by parts. Scenario 2 is where like you have to use the fact that one is hidden, right? Like there's a secret one so that you actually get a product and not just like, because like it's kind of like missing a product structure, right? Like so you kind of insert the product by brute force. And then scenario 3 is where like you kind of break one of the factors, so like you can like you can kind of like facilitate the integration of the other factor. And in scenario 4 is where like it's kind of also like again there are no tricks except that you go back to where you started and then you kind of like put that back together, right? I
so
guess.
those scenarios are we like signing?
I mean, you do need them, right? Like that's a good point. You do need them something like the nice thing about like sines and cosines, right? It's like it kind of like they alternate like their derivatives, right? Derivative of sine is cosine and the derivative of cosine is minus sine, so they're more or less like the same. But yeah, so like I like in general, if it has something trigonometric, that is like a good like metric to look for. But it also like if this had like x cubed sine of x, then it wouldn't work the same way because every time you take a derivative of x cubed, that kind of drops, right? So 3x squared and then 6, like so that keeps going down. The thing with is that e to the x also has like this magical property that it kind of like stays the same as you take derivatives or integrals. So that's why you can return to where you started because like it didn't get simplified. But yeah, so do you need like a kind of like a specific combinations of sines and cosines for this one to realistically appear in the types of problems, in fact, spoiler alert, like, towards the end of the course, we will, once we talk about complex numbers, there is a relation between sine and cosines, where you can write like sines in terms of cosines. Or sorry, where you can write, obviously there's a relation between sines and cosines because those are like periodic and whatever. There's a relation between sines and e to the x. That's what I was trying to say. And you can write the sine and the cosines in terms of exponentials. And that's kind of called like Euler's formula. And that's like an important thing. But let's finish here. But yeah, those are like the 4 examples. So like on the workshop, I'll put like for today, like this week's workshop, it will be more like similar to this, like integration by part formulas, like also something about surface areas. But like, yeah, if you master these 4 scenarios, like you mastered like all the problems. Yeah. Oh yeah. This one like of the breaking. Mm-hmm. I also shared them like the